Okay, so in the in-class data folder, you'll see this two population hypothesis testing blank file. There's also a completed file, which hopefully when we're done today, will be pretty close to having completed everything. The last slide in the PowerPoints, week 12 lectures, has these three questions, right? So the first one is assume that we know population variances of enrollment in Midwest and Southern universities. So we've got data on the enrollment at Midwest and Southern universities. We somehow know the population variance in those enrollments. And so we'll think about these as two populations. One is the Midwest, one is Southern universities. So do Midwestern schools have on average larger or greater enrollment? Right? And then the next question, do Southern schools on average have a greater proportion of schools that have more female than male students than in the Midwest? And then is there a difference between male and female BMI, assuming we only have sample variances? Right? So three different types of examples that we've talked about. Right? We could do all three of them by hand, but we have the data in Excel. Let's see how we could do this in Excel and how much easier it would be. Right? So we've got these 5 data sheets. The very first one we had South and Midwest. Right? So the Southern one, if we look at the Southern data sheet, we could do, or no, sorry, Midwest. The Midwest data sheet is the one that we want to start with, right? So I can do the enrollment and I can do the proportion of schools that have more female than male students. Right? So two types of examples, but I'll calculate both of these on this sheet first before we go to the Southern sheet. So what would be the average enrollment? Well, hopefully, or the mean enrollment, we just have to take the average of total enrollment, right? And all of these schools that I pulled out are Midwestern. So it looks like we got actually Ball State here as the first one, right? And I think, you can kind of see all the different universities here. So then I hit, and maybe you don't agree completely with my definition, like I included Missouri in the Midwest and Kansas, but we could argue over that a little bit, but for the most part, I think this is a pretty good division, right? So we've got the sample mean. Let's assume we knew that the population variances are. So did I give you the assumed true? Oh, they're in the. Let's see to make sure that these numbers match up with the other one that I provided. And this will open this up. So we'll go over here. So I did what? I'll copy this over. Population variance of 75. 1, 2, 3, 1, 2, 3. So 75 million. Okay. So let's assume that's the population variance. And then the Southern sheet, where we have the Southern data, here's schools in the South, I'm going to actually put in the population variance here as well. So if we check from the complete one, what did I give the assumption? The assumed true was 62 million for the population variance in the South. So let me just plug those numbers in here real quick for us. So if you're on the Southern data sheet, put in 62 million as the population variance here, and for the Midwest, the population variance is 75 million. Right? If we're assuming that this is only sample data, this is one of those ones where it's weird that we would have the population variances, but if for some reason we did and they were given to us like this, like they would have to be given to us. So if you're thinking, where does the 75 and 62 million come from? I'm just saying assume that you know that somehow. Someone tells you that information, right? Probably not a realistic thing with this enrollment example, but more so like if we had production or we knew the machinery had a certain variance on it. Well, what's my sample size? Well, the equation we use for that is just count. So I'll count the total number of observations I have here for enrollment. Cool. Now I'll do the proportion of schools here as well. We'll hold off on that. I'll walk each one. So the very first one was, is there just difference in Midwest and Southern enrollment? So we have the mean, population variance, sample mean, sample size for the Midwest enrollment. We can do the same thing for the South, right? So I'm gonna just bold this as we walk through, kind of separate it a little bit. So for the South, my sample mean is the average, take the mean of this total enrollment variable, Control Shift or Command Shift on a Mac, down arrow, selects every single cell. Should have mentioned that one before. Sample size, we'll do count, click on that first observation, Control Shift or Command Shift on a Mac, down arrow, hit enter. Now we've got sample mean, sample size, and population variance. Well, now we had the data for the Midwest, right? The mean, sample size, and population variance on a different sheet. And we haven't done this yet, but one nice thing you can do, it makes life a little bit easier instead of copying these over by hand. If you have it on a different worksheet within the workbook, I can just put an equal sign, click on that worksheet, and then click on the cell. Now notice, the way that it does this is, it is in M4, but M4 of what? On the Midwest sheet, right? So putting Midwest and the exclamation point, that identifies I'm going to the Midwest sheet within this workbook. I hit enter, and now, because I wanted the next two, right? If I copy this down, it's going to update my cell reference to grab those next two cells in that sheet. So now I've got the sample mean, sample size, and population variance for both the South and the Midwest. Okay? So I want to do this confidence interval. I could do confidence intervals or hypothesis testing. Right? And let me zoom in a little bit here. Okay, so we can see this a little bit better. And here, these are just put this in scientific notation. We could go to format cells, and maybe I just want a number. I'll keep these, and then we'll go here. There we go, so you can kind of see those in there. It's okay if they're in scientific notation, but just to make this a little bit easier, I put there. So we're going to do this confidence interval for the difference between South and Midwest enrollment, right? And I think the way that I phrased this test, right, was do Midwest schools on average have a greater enrollment? So let's do Midwest minus the South. So usually, what I should kind of do here to just make it match up to make it a little bit easier for you guys, let's look for the difference between in Midwest and Southern. Oh, wait. Here we go. That was for the proportions. This one is for, oh, there it is. Let's just change the ordering around just to be more consistent with the question that I put in the slides. Right? So we're going to look at the difference between Midwest and the South. So what we're going to do here is we go back, maybe in the slides, or as we get closer to that other exam, I'll pull up a third formula sheet. And what we're going to do is we're going to say, okay, we're going to build a confidence interval. And here we have Midwest minus the South. So we've got our sample means. Oh, if I can get this to, oh, it does this sometimes. Autofocus. We'll switch back. Sometimes that helps. There we go. So we'll take that difference in sample means. That's going to be where we center our confidence interval. We have these values in Excel. We have population variances, so we can use that standard norm or Z table. And then here we multiply by, and what this represents is the standard deviation between, or standard deviation for the difference between those sample means. So how do we do that? We took each group's population variance, divided it by its sample size. So for this would be for the Midwest, and then do the same thing, but for the South. Right? We have all these pieces in Excel. We can use Excel to find this. Okay. So how do we use Excel to find this? Well, I could actually do many different confidence levels. So I think I accidentally erased that word. So we've got alpha here of 0.1, 0.05, and 0.01. So we want the Z value that gives us alpha over 2 on each side of our confidence interval. So when we know the area that we want in the tail, and we want to find the Z value that gives that to us, we're working in reverse or inverse. So we use that norm.s.inv. Okay? Now what area did we want? Well, we want alpha over 2. Right? But we kind of mentioned, like if I look this up in the table, if I look up alpha over 2, I'm always going to find the negative value of that Z value that I want, because the negative and positive are already built into that confidence interval equation, right? We subtract to get the lower bound, we add to get the upper bound. So I can do this, but it's going to give me the negative Z value that I want. So there's two ways I can work around this. One, I think maybe is easier, is just take the absolute value of that, which basically drops the, whoops, I need another parentheses over here, which basically just drops the negative sign. Now the other way I could do it is instead of taking the absolute value, I know that if alpha over 2, right, is in the left tail, and that gives me a z-value, I think is of negative 1.64, then the other side, right, is a symmetric distribution. If I want the area in the upper right tail to also be 0.05, it would be the same z-value, but positive. So I have alpha over 2 in the upper right tail. What would be to the left of that? 1 minus alpha over 2. And that would give me positive 1.644 as well. Right? So I'll give you maybe a visual that kind of helps with that. So let's say, right, I'm trying to find this z-value. You can kind of think about this. That gives me alpha over 2 in each tail. Right? So I want this negative z-value gives me the lower bound. The positive z-value gives me the upper bound. So I could have looked up alpha over 2, and it told me, right, alpha over 2 being 0.05, told me negative 1.64 about. Well, if I want 0.05 in this tail, what would be to the left of that z-score? Well, it'd be 1 minus that, so 1 minus alpha over 2. Okay? So that's where that came from. All right. So I've got my z-value. If I wanted to, for different levels of alpha, I could just copy this down, and then it's going to update that cell reference to the next alpha value. Okay? So I've got my z-values for the 3 different levels, and I could build 3 different confidence intervals. At this point, it's really just using Excel to be the calculator for you. So I would do equals, take the difference in my sample means, and I believe the way that we set this up was the Midwest minus the South. Right? For the lower bound, I will subtract that z-value multiplied by the square root of, the square root of the Midwest's population variance divided by, hold on, Lapua. So we'll take the Midwest population variance divided by the Midwest sample size. We'll add to that the South's population variance divided by its sample size. Right? We're really just using Excel as a calculator here. And instead of typing these numbers into a calculator, we can just basically select them. Right? Now, when I copy this down, I want everything to stay the same except for this z-value. So what I'm going to do, I'm going to go ahead and select these. And if you're on, so I think for me it's going to be FN F4. So if you're on a laptop, sometimes there's an FN key. So the shortcut is select what you want to put dollar signs around, hit FN and F4. If you're on a regular desktop or you don't have an FN key, you can just hit F4 and it should put those dollar signs there. And I think for a Mac, it is Command T that you have to hit to put those dollar signs around. I'll do that for here as well. Or you can do it manually. Here. There we go. Now the only thing we don't want to lock in or freeze or put dollar signs in front of is that z-value, because we want that as I copy this down, we want it to kind of update. But everything in terms of the sample mean, population variance, sample size, that stays the same. So we hit enter. I can copy this down, and I've got my kind of 3 lower bounds. Okay. Did I put something in wrong here? The square root of, no, we're good. Now we can do the same thing for the upper bound. It's going to be the same equation, but an addition sign. So what I always do, I think is easiest, go up to this bar up here once you select on that lower bound, copy, and then to get out of this cell, I'll hit enter, and then go over to my upper bound. I go up to this formula bar, and I can paste. So it doesn't update any of my cell references if I copy and paste in this way. If I like drag it across to copy, then it updates that cell reference for the z-score over 1. So now I just go, I change that negative to a positive sign because that's the only difference to get, between the lower bound and upper bound equation. Now I can copy this down, and I've got my lower and upper bound for these 3 different levels of alpha. Notice, as I go to higher levels of confidence, so this was like the 90, 95, 99% levels of confidence, which correspond to alphas of 0.1, 0.05, 0.01. At higher levels of confidence, I have to widen the range of values. So notice this is my smallest interval, my lower bound starts to get lower. When I want to say things at a higher level of confidence, my upper bound starts to get higher. Right? So we didn't make a glaring mistake there. And it should be that the difference in these salaries of what, about 4,000 should look like they're kind of in the middle of these, and sure enough, they are. Okay. So that's how we do confidence intervals. Right. Well, it should look pretty similar to what we did with one population, but slightly different, slightly more moving parts in these equations, but the same process. So now we'll go down to hypothesis testing. So let's say, once again, let's do the difference between Midwest and Southern. We want to know, is this difference positive, right? So if we want to know, is this difference positive, and I'm going to actually build a little bit more here. Cancel. So I've got, is the assumed true difference, basically, I'm assuming the difference is 0, which would make my alternative hypothesis. So if I wanted to copy this, my alternative hypothesis would just be, is it, and here we go to design, there should be a not equals to sign right there. All right. Oh. All right, my alternative would be that difference is not equal to 0. So I have a two-tailed test here. So, oh wait, I might be remembering this wrong. Oh, sorry, I don't want to do a two-tailed test here. I want to do let me make sure. I thought that I set up one of these. Okay, this one is, so we are doing a two-tailed test here, right? So let me phrase this as, well, I'm going to change this on the fly. I'm going to change this on the fly so we get an example of every single kind. I'm going to do a right-tailed test here. So what I'm actually going to do, I'll change this complete Excel file. I'm actually going to do, we want to test is that difference greater than 0. So I'll assume the opposite, which is that it is less than or equal to. So I'll update that complete version of the slides so that we have an example of every single type of tailed test. So here we're going to have a greater than sign in the alternative, so a right-tailed test. We want to know, is the Midwest greater than the South? Okay. So we assume the opposite is true. So how will I find that test statistic, which if I know the population variance is, it'll be a z value, right? Z statistic. So I take the difference, right? If we go back to these slides, this is what we did yesterday. Let's see if we can find the test statistic up here. Where are we at? Here we go. Here was our test statistic equation. So we take the difference in our two sample means. We have the assumed true difference, which is a 0. And then we have population variances, sample sizes down here. Pretty easy to just use Excel as a calculator to do this. So we'll take the difference between the Midwest, so Midwest minus the South's sample mean. We don't really have to subtract that assumed true difference of 0, although we could. We could do minus 0 here. Okay. Now, what I'm actually going to do, so we won't put that in there for a second. Right? We don't need, we'll put it in there just to be complete, minus 0. And I'll show you something else we could do in this after we get this done. We then divide by the square root of each group's, so we'll take the Midwest's population variance divided by its sample size. Add to that the other group's population variance divided by its sample size, right? So we've got our test statistic equation right here, okay? This will be our test statistic. How do we find the p-value? Well, if this is a greater than or a right-tailed test, when we're looking for the p-value, what we're really doing is we've got what was it, 2.6. The area to the right for a one-tailed right-tailed test, this is our p-value. So we want to find the area to the right of 2.6. Okay. So how do I do that? Well, I now know the z-value and I want to find the area to the right of it. Well, I have an equation in Excel that'll tell me the area to the left. And if I know the area to the left of a z-value, the area to the right would just be 1 minus that. So I can do equals 1 minus norm.s.dist, use that standard normal distribution, look up this z value, this z statistic, comma 1, tell me the area to the left of it, and then when I subtract that from 1, it gives me the area to the right, which represented my p-value. Right? So when I'm doing a right-tailed test, I can use this norm.s.dist function, but that gives me the area to the left, so I have to subtract that from 1 to find the area to the right. So I've got my p-value. It looks like it's pretty low. Right? So if I wanted to compare this to really any alpha, it's less than 0.1, it's less than 0.05, it's less than 0.01. I should be rejecting at every level. Okay? I could also come up with critical values. Right? Now I say values here because I'm going to do it for 3 different levels of alpha. So what I could do is, I'm using that standard normal distribution. I want alpha in my upper right tail, so there's 2 ways I could do this. Right? I'll show you the board here once again. Oops, there we go. So if I'm looking at a 2-tailed test, or sorry, a 1-tailed test, I'm jumping ahead of myself. So we've got a 1-tailed test, and it's a right-tailed test. And I want an alpha of 0.1 in that right tail. So if I'm looking for the critical value, it is what value gives me 0.1 in the upper right tail. Well, when I use Excel, I can use this norm.s.inv, but the probability I tell it is the area to the left. So if I want 0.1 to the right, the area I want to the left would actually be 1 minus that. Or I know that it's a symmetric distribution, so I could look up the area of 0.1 and just know that I'd be finding the negative value of what I wanted. So similar to confidence intervals, what we could actually do here, we'll do it 2 different ways. So the first way I could say, we'll just look up this alpha, and then I'll have to remember, oh yeah, it's going to give me a negative value, but it's a right-tailed test, so I want that value, but positive, so just take the absolute value of it. I could do that, and that'd be fine. Or I could say, well, look, what I actually want to do is, I know the area to the right that I want, so the area to the left would just be 1 minus that. So 1 minus, norm.s.inv, just 1 minus whatever the area in the right I want is, which would be alpha. So both ways should give me the same value. Okay. Once again, I can just copy this down, and it'll update that cell reference and use the new alpha value. So I've got my critical values here. So I think I showed you how to do this with p-values. And you don't have to do this in the assignment. You can simply put whether or not you reject. And you could do that with either looking at the p-value and comparing it to the alphas. Or you could say, is my test statistic, right, greater than my critical values? Because if it's greater than, it would fall in the rejection region. So you could say is equals if my test statistic is greater than my critical value. If that's true, so here's what I'm checking, is the test statistic greater than my critical value, comma, if it's true, put the word reject, and you have to put that in quotations to let Excel know this is text. If it's false, then I would fail to, reject. Close the parenthesis. Now when I copy this down, I want to use the next critical value, but I always want the test statistic to stay the same, so I'll put some $signs in front of that so that cell reference doesn't change. Now when I copy this down, I reject at every single level. But notice, what's cool about this if statement is, like, let's say, let's just for instance say this is instead 1.96. Notice it kind of compares this, oh, I rejected these 2 but not this one, right? So I'll hit Control Z, so put back what should be in there, but I'm just kind of showing you, for some reason, things changed here, we could look at different levels. So here, with 90, 95, and 99% confidence, or 10, 5, 1% significance, we can reject that the true difference between the Midwest and South enrollment is 0. That there is actually, we found significant evidence that there is actually a difference. Now, when we said, is this difference greater than 0? Well, if we look at the actual difference, it's like 4,000. So maybe I say, well, okay, I've got pretty strong evidence that there is a difference, that the Midwest does have a larger enrollment than the South. But how much larger? Is it 2,000 people larger? Right? So instead of using 0, we could say, is the difference greater than 2,000? Right? So I would assume the opposite is true. We've got the same kind of setup, but actually, for my test statistic, I no longer have an assumed true value of 0. I have an assumed true value of 2,000. Now, what I probably would actually want to do here is, I'll delete this, and put my 2,000 in this cell, because now, instead of typing in a new value every single time, instead of 0, I want whatever value is in this cell. Okay. Now, see, automatically updates, so now I fail to reject, right? I don't have enough evidence that says that the enrollment is more than 2,000, right? So I did find that, yeah, the enrollment is quite a bit higher, but there's a really large variance, right? It could just be the sample of schools that I have. And I could play around with this. Well, can I say it's greater than, 1,000? Change this to 1,000. Well, I could at the 90 and 95% levels, right? And so we could play around with what values we can reject and what values we could fail to reject. And what should be true, well, I'll hold off on that. So that's how we do a hypothesis test, right? So the next type of example we had was, I'll go down here. Do Southern schools on average have a greater proportion of schools with more female students than male students than the Midwest does? Okay? So we had a right tail test here. I'm going to change this one to say it's basically the same thing. So do Southern schools on average have a greater proportion? You could also think about this as, does the Midwest have fewer or have less than? So we're still going to define this as Midwest minus the South. So if Midwest minus the South, if the Midwest has fewer, is that difference less than 0? Okay. So I'm going to save this here. So we're saying, does the Southern have a greater portion of schools that have more male than female students? Or conversely, does the Midwest have fewer schools? Right? So when we're thinking about the difference here, what I'm thinking about is that difference in proportions. So we're going to take the proportion in the Midwest minus the proportion in the South. We're saying, is this one less than this one? So if that was the case, then this difference would be less than 0. That's what we want to test for. So we assume the opposite is true, and actually we don't have the samples here. We're actually looking at is the population difference. So we assume the opposite is true, there's a greater than or equal 0. So you have a less than sign in the alternative or a left-tailed test. So automatically we should be thinking about left-tailed test. I'm going to have negative critical values. Okay. So if we go back to Excel, how can I find this? Well, let's go to the Midwest sheet first. I can use this data and say, okay, this variable identified, did the school have more female than male students? So if I have a 1-0 variable, I can find the proportion of schools that have more female than male students by just taking the average of that binary or 1-0 variable. So I'll take the average of this 1-0 variable, that'll give me the sample proportion. So 75% of schools in the Midwest have more female than male students. Right? If I then look at the sample size, so equals count, select this. Okay? I then go to the South, and I say, okay, in the South, how many schools have more female than male? I go to that variable, select it. Ooh, about 85%. Right? So once again, just the average of that binary variable. Okay? I'll do an equals count to find the sample size, how many schools I have from the South, Control Shift or Command Shift if you're on a Mac down arrow. So now I've got the sample portion sample size from the South. I had the other variables for the Midwest on the other sheet, so I put equal sign, select that sheet, select where that sample proportion was, hit enter, copy that down to get the sample size. So same kind of thing I did for the sample means, but I'm just looking at a sample proportion now. So if I want to do the confidence interval here, what should be true is, well, I'm looking at the same alpha over 2 on either side of the confidence interval. If I'm using that standard normal distribution, the z-value should be the exact same. So here, up here, I did it with 1 minus alpha over 2. I said the other way we could do it just to give you an example, is this absolute value. So I could have taken the absolute value of norm.s.inv of alpha over 2. And if what I told you was correct, whoops, hopefully we get the exact same 3 z values when I copy this down. Sure enough, we do. Right? And that should always be the case. Right? So as long as I'm building these confidence intervals, should always be able to get the same 3 z values to build those. Once again, now I'm basically using Excel to be a calculator. So if I go back yesterday, we talked about confidence intervals. How far down do we have to go here? Get close. There we go. There we go. Here's my confidence interval equation for sample proportions. I'm going to use Excel basically I'm going to have these sample proportions I can click on, sample sizes, and then I looked up those z values, right? So, how do I get the lower bound? I'm going to take the difference in those sample proportions, so Midwest minus the South. Right? I'm then going to subtract the z value multiplied by the square root of the first group sample proportion times 1 minus the first group's sample proportion divided by the sample size. Then add to that the second group sample proportion times 1 minus that group sample proportion divided by its sample size. Okay? So really all I did here was use Excel as a calculator, right, to type in what that confidence interval equation was. Now when I copy this down, I don't want anything to change other than that z value. So once again, I can select my cell references, hit your Command T if you're on a Mac, Fn, F4, or just if you don't have an Fn key, just F4. I'll do the same thing, selecting these cell references. Right? So now when I copy this down, nothing will change except for that z value. Right? So I hit enter. I could do this a little bit different than I did before. Instead of copying this down right away, I know that I want the upper bound to be this exact same equation, so I'll copy that, hit enter, go to my upper bound, paste it into my formula bar up here. The only thing that changes is I want well, it's probably hard for you to see that. Instead of a negative sign here, I want to add a margin of error, so I'll add that, hit enter. Now when I copy these down, the only thing that changes is that z value, right? Because I'm building confidence intervals for 3 different levels of alpha, which would correspond to 3 different z values that I would need. And I've got my lower and upper bound here. Right? Notice I keep using these same values. So pretty easy, pretty similar to what we did before. It's just once you get to this point, you're just using Excel to be a calculator for you. Now I can do a hypothesis test for proportions as well, right? And now let's say, I'm going to copy this over. What I want now, oh, that's not what I wanted. Doesn't look as pretty. Oh, I should be able to copy, paste, there we go. So now I want to know, is that difference for my alternative hypothesis? I said, is that a negative difference? So for the alternative hypothesis, it's going to be, is it less than 0? Which would then mean, control, paste that up here. For my null hypothesis, I want to say, I assume the opposite is true, which is that it's greater than or equal to 0. Not 0. There we go. Okay. So I've got the alternative hypothesis a negative sign, so it's a less than or a left-tailed test. Right. What do I need to do? Well, I can find critical values, but what's going to be true is, it's going to be these exact same values I had before. It's just now for a left-tailed test, they're going to be negative. Right? So I can find the critical values here. In fact, let me just copy this, paste it over here. Now these aren't going to be the same, they're going to be something different. And I have the same if statements, those will still be okay. Actually, I'm going to have to select different cells, so we'll delete all that, just use the alpha. So how do I find the critical values? What's what gives me alpha in my tail? Well, now I'm just looking at the left side, so now I can just do norm.s.inv. The area I want in the left tail is alpha. Hit enter, copy this down. I've got my 3 critical values. They should be the exact same I found before, but now they're negative for a left-tailed test. Okay. How do I find my test statistic for a proportion? Well, this is the one where we said we have a little bit more work to do. So let's see, how far do we have to go until we did that? Right here, where we had the intermediate step where we had to calculate p-bar. So I'm really just going to enter this into a cell and then enter this formula into another cell. Okay, so for that p-bar, it was take the first groups. Let's see if I can get this all to be on one page for you. I don't know if I'm going to be able to. Shoot. There we go. Take the first group's sample proportion, multiply that by that group's sample size, add to that the second group's sample proportion times its sample size, then take all of that, so put that in parentheses, and divide it by the sum of those 2 sample sizes. I believe that's what the equation is. I'll double check it. All right. So I hit enter. I've got my p-bar. I'll just double check. So yep, that's what it was. Now once I have p-bar, I can plug it into my test statistic equation. So I go back here. To get my test statistic, I will look for the difference between the Midwest and the South, right? And that's how I had it set up. So Midwest minus South. I then will subtract the assumed true difference, which for now is just 0. But I'll show you we could change that. And I would update our test statistic. So that's my numerator. I divide that by the square root of. Oh, why isn't it like that? Stop it. The square root of. I want to select this, what's in p-bar, but for some reason this is too large here. I'm going to hit enter here. Go back into this cell. Why is it not liking this? I'm going to copy this over. So it's what? S22. I can just put it in there manually. So we'll divide by the square root of S22 times 1 minus S22. Then multiply that by 1 over the sample size of the first group plus 1 divided by sample size from the second group. Okay. So it is a little bit tough to kind of put all this in, but it's really just using Excel to be a calculator for us. Okay. So once I have that entered in there, I'll actually I think I need one more parentheses. Yep, to close it. Hit enter. I've got my test statistic. Okay. So I then say, okay, what would my p-value be? Well, for a left-tailed test, the area that's more extreme than my test statistic will be the area to the left, right? So area to the left, right, we've got our test statistic of like negative 1.4. We want the area to the left. So I can use that norm.s.dist function. So norm.s.dist, tell it my test statistic, comma 1, and it would give me the area to the left. Okay. All right. So that will give me my p-value for a left-tailed test. So I've got my p-value here. I've got my critical values. Now to make my rejection decision, I could do the same thing I did before. It's just now instead of is my test statistic greater than the critical value, I would have to say is the absolute value of my test statistic greater than the absolute value of my critical value. Now one way I think it's easier is if I use my p-value, I never have to worry about kind of direction. It's always is my p-value less than alpha. So what I could do is use that if statement and say if that p-value is less than alpha, right, comma, if it's true, put the word reject here, and then comma, if it's false, put the word, well, we'll do the whole thing, fail to reject here. Now when I copy this down, I want to use different levels of alpha, but I want to keep using the same p-value, so I'll freeze that p-value. Okay. Hit enter, we'll copy this down, and I've got my rejection decision. So the 90% level, I can say that the Midwest has a lower proportion of schools that have more female than male students enrolled, but I can't say that there's any difference at the 95 or 99% level. Okay? So that's kind of our first two examples. We've got one more. Okay, so we've got through the first two, we got one more. So for this one, we're going to use a different data sheet. Right? So go back here. The final question that I have is there a difference in male and female BMI? So here, is there a difference? Are they just different from each other? We're going to have a two-tailed test. Right? But we only have the sample variances, so it's going to look more like what we did in today's lecture. So we'll go to this male and female data sheet. And the female data, right, I already have calculated for you, so we don't have to do it again. The mean, the variance, sample variance, and the sample size for female BMI. Then we can go to the male data sheet. I'm going to increase the zoom a little bit so it's easier for you to see as we walk through this. So once again, I can get the mean, variance, and sample size. So average gives me the mean. I'll select the BMI variable, Control Shift or Command Shift down arrow, Command Shift up here on a Mac. Get the sample variance, var.s, select my data. I'm going through this pretty quick, but we should be pretty familiar with this at this point. Get my sample size equals count and select that data. Okay. I've got the mean, variance, and sample size on the female data sheet, so I go equals, and then I select that. Copy this down, just like we kind of did before when we were dealing with the Midwest and the South. Right? So I've got everything I need here. Right? The mean, the sample variance, sample mean, sample size. Now, what I'm going to do on your Excel assignment is similar to what I've done in this. Right? So I've got, well, actually I just copied and pasted here, let me see, I think on the complete version, let's see, I have the actual equation in here. So I don't. I'll show you an example here real quick. Oh, I don't know if I have one. So on the Excel assignment, what I'll have in here, I think when I copied this over, I forgot to copy the formulas when I was copying and pasting some things together. I'll have the actual formula for the degrees of freedom, which was, right, this guy right here. So that as long as you, in the cells that I've like kind of created here, as long as you find the mean, variance, and sample size in these cells, it would automatically compute this degrees of freedom for you. So let's see if I can actually do this now. Let's see if I can reproduce the exact same value. So let's do equals the first sample variance divided by the sample size. And you won't ever have to do this, so don't worry, because things will start to get counted. So then I square that. I then divide that by this first sample variance divided by the sample size squared, and that gets divided by sample size minus 1. And then I add to that second group's sample variance over its sample size. I square that and I divide that by its sample size minus 1. Well, let's see if I can get the same value. Whew. All right, so it's not fun to type in, but when I put this on your homework assignment, it'll have this already typed in there for you. So as long as you get the correct answers in here, it'll automatically put that degrees of freedom in. And then what should be in here is we want to floor this number. I think it's comma, what was it, 1? Yep, it's an integer. So once you fill these in, it should automatically update this. And I'll repost this complete version here in a second. So let's copy that onto our blank version. Formulas. Perfect. So now we got the formulas in there. All right, so how do we do confidence intervals? It's the exact same thing that we did before with sample means. The only difference is instead of using the norm.s.inv here, what we're dealing with a student t distribution, so we have to use t.inv. If we have a two-tailed test, we want the t value, right, that gives us alpha over 2 on either side. So it's alpha over 2, right, on either side. And then comma, here's our degrees of freedom, right? Now, because we're dealing alpha over 2, it's always going to give us the negative value. So we said one way we can fix that is just take the absolute value, right? So we get our t value. When I copy this down, I want alpha, the cell reference for alpha, to update, but I don't want the degrees of freedom to update, right? I want to keep using the same degrees of freedom, so I'll freeze that. Okay. So I hit enter. I can then copy this down. Now notice these are really, really close to the z values that we were finding over here, but they should be because we have really large sample sizes and we have a high degrees of freedom. Remember, as the degrees of freedom gets higher and higher, we get a closer and closer approximation of the standard normal, and so this is going to be really close to our z value. Okay? Now to get the lower bound, we just take the difference between the two groups' means, so male minus female. For the lower bound, we subtract the t value multiplied by the square root of each group's sample variance divided by its sample size. So we're going to do this. Now we said when we copy this down, we only want the t value to change, so we have to freeze these. So once again, your F4, or if on a Mac, your Command T. So we'll freeze these, put dollar signs in front of them. Now we can copy this down to get our lower bound. If we want to copy this over, we don't want that cell reference here, K12, to update, so we can just copy, hit enter to get out of the cell, paste. Oh, that's not what I want to do. That is. And then instead of subtract the margin of error, we change that to we want to add it. Right? Now I can copy this down. I get my confidence intervals here. Okay, pretty easy. Same process we were doing before. It's just we had to find this t value, which not only needed alpha over 2, we also had to tell our degrees of freedom. Okay. So what if we do a two-tailed test? So I'll plug in here for the female, or for the, let me kind of use this and cheat. We'll copy this. So we'll kind of remind you for a two-tailed test, what we're going to do is the value equal to 0, which would mean the alternative hypothesis would be, is it not equal to 0? Okay. Well, how would I get my test statistic? Well, we went over that equation earlier today. So if we look at the PowerPoint slides, here's our test statistic equation. We're just going to basically use Excel to be a calculator and enter this in. Okay. So that test statistic is take your sample mean from the first group minus the sample mean from the second, subtract the assumed true difference, which we had here is just 0, and I'll show you in just a second what we can do, play around with that. Divide by the square root of each group's sample variance divided by its sample size, right? And that would give us our test statistic. So we'll hit enter here. We got negative 2.36. How do I find the p-value? Well, for a two-tailed test, if we found the negative test statistic, the area more extreme than that is the area to the left, right? More extreme would be a larger negative value. So we can use that t dot dist, right? We can tell it our test statistic, comma, tell it your degrees of freedom, which is up there, and then comma 1, telling it it's cumulative, look for the area to the left. Now, what we would then need to do is, well, we have a two-tailed test, so this is the area that's in the left tail. What about the area in the right tail? It's the same, so we can multiply it by 2 to get the total p-value. Right? Now, I could have also done this differently. So there's a t dot dis dot 2t. Right? Now, I don't really like using this, and I'll show you why. I like doing the multiply by 2 just because that's kind of how you have to do it by hand. But also, if you use this dot 2t with a t distribution, if I select my test statistic and then put comma my degrees of freedom, what it's going to try to do is it's going to try to look up this test statistic, find the area that's to the left of it, and multiply it by 2. But the way that this formula works is it actually needs to look at the right side of the distribution. So if I hit enter here, it doesn't do anything. So what it actually needs to do, well, it wants this test statistic, but it can't deal with the left side of the distribution. It can only deal with the right side. So you actually have to use the absolute value of your test statistic when you put it into this function. And now if you do that, now it'll work. So it's a little finicky, and because you can get a negative test statistic for a two-tailed test, I just kind of always default by finding the area in the tail and then multiply by 2, because that's how you do it by hand as well. Okay? So that is how we would find our p-value. We could do critical values. the critical values are really going to be the exact same as what we did with confidence intervals, right? Because we want alpha over 2 in each tail, right? And where we have the same degrees of freedom, so we would actually find these 3 values for our critical values, and they would be pairs as well, right? So I think, let me double check, I don't think I put those in completed version. So I looked up one specific critical value here. So the completed version, I think I don't have the formula, so I'm gonna have to update that so you guys can see those. But we're walking through it today, so that's good, right? So I could do, how do I find the critical value? I'm just gonna do it for one level. So equals, if I know the area in the tail, and I'm working backwards, it's t dot inv. The area I want, let's say I had an alpha of, let's do a 99% level, right? So the 99% level, my alpha is 0.01, but there's half of it in each tail, so divide that by 2, and my degrees of freedom is up here. So that should give me my negative critical value. If I have a two-tailed test, I want to indicate that there's also a positive critical value. I'll do the absolute value of what? This is K19, right? And so I can show I have 2 critical values here. And then this was just that I can calculate the p-value 2 different ways. Okay. Now there is one thing that we can do in Excel that kind of helps us. If we have sample variances, we can use a t.test shortcut. So that t.test shortcut says, okay, look, tell me the 2 groups you want to compare. I will calculate the sample mean, the sample variance, and the sample size behind the scenes. I'll also calculate the degrees of freedom. And then if you tell me the number of tails for the type of test you're doing, and you tell me what this t.test can do a couple different examples. So the one that we're going to want to use is always, so here, I'll select it first. So first, what's your first array of data? Well, ours was, we did males minus females, so take male BMI, so select that as your array 1. Put comma, right? And you might have to scroll up to the top here, just so you can see this. So, oops, we select, stop it. Okay, why is this putting this here? I don't like this. I don't want the help. There we go. So we selected the first column of data. Now we need to put the second column. Well, the second column was on the female data sheet. So now select female BMI. Once you've selected that, right, Control Shift or Command Shift down arrow, put a comma, go back to the male data sheet. Now, I don't really want this here. You can keep it here and be fine, but we don't really need to tell it data for the third thing. The third thing is how many tails. Right? So here we have a 2-tailed test, so put 2. And then comma, what type of example do you have? So on next week, we'll do matched pairs, which is what this one is. But for today, we're doing a 2 sample where we don't have the same variance, right? It's very unlikely. We won't actually use any examples in this class where we have to do a 2 sample equal variance. We're not going to ever use that in this class. More often than not, we're going to have 2 samples with unequal variances. And so the type of t.test we want to, like built-in t.test we want to use is comma 3 here, okay? Because we have 2 sample means that have different variances, right? So now that I've got that entered in, it's going to do all the work for me, and it's going to return me my p-value. So notice this is formatted a little bit differently, but it's the exact same p-value I found if I did it step by step. Right? It just does all the work for me. So that's kind of a nice shortcut, so we don't have to do this all by hand, and it saves us a lot of space in Excel. Right? So there, in your Excel assignment, I will ask you to do it this way, and then I will ask you also to use the t.test. All right, so I want to see that you can do it both ways, partially because it's good going forward to know how to use this shortcut, but it does have some limitations that we'll kind of stumble across here, which is, well, look, what this t.test does is it always uses the assumed true difference of 0. What happens if I want to use an assumed true difference something other than 0? So here I just said, is the BMI different? But maybe I want to say, is female BMI and male BMI, is it different by more than, I don't know, 0.2, right? Well, if I do that, that's going to change my test statistic, which will change my p-value. But notice there's no option in t.test for me to change that assumed true difference. So it can only compare to that assumed true difference of 0, right? So it's a little bit limited, so we need to know how to do it by hand, kind of do the intermediate steps as well. just in case we want to do something other than 0 here for the assumed true difference. All right. So that's kind of one of each type of example. I think this should be a pretty good place to start for, this could get you pretty far into the Excel assignment. I'll get that posted later this afternoon. We haven't done matched pairs yet, which is what this final kind of worksheet is for. I'll get a complete version kind of updated with, so it matches exactly what I did today, because I did a couple things on the fly. I'll get that updated. Also, you could do a difference in the sample proportions here for, difference between, what is that new kind of race here? I believe that's what it was. I'll look at the complete version. I think it had a difference between, male and females that were white or versus non-white. So it's just a different example of comparing sample proportions. I'm not going to walk through that here in the video, but it'll be an additional example that you'll have in that complete version of the Excel document as well. Okay. All right. So that concludes this kind of help file for how we do 2 population tests in Excel. We saw one of each type of example, right? One where we did confidence intervals and we did a hypothesis test for the differences in sample means when we knew population variances. We did a confidence intervals and a hypothesis test for the difference in proportions, and this is definitely spelled wrong, so let's fix that. Proportions. And then we did one where we did confidence intervals and hypothesis testing for sample means when we only had sample variances. So that should get you through the majority of the next Excel assignment. If you have any questions on that, please feel free to reach out. I want to make sure everyone kind of does pretty well. And it's a really similar principles to what we did with one population. So it should be, if you did Excel 3, you should be somewhat used to kind of how we do this. The equations for the confidence intervals and the test statistics changed a little bit. But in terms of finding critical values and p-values, really nothing has changed there from what we did with one population.